So yeah, please welcome Drona sorry if I say your name wrong, Drona Vatsyayan,
Yeah, yeah.
um, joining us from Valencia, who will be talking about large interior masses and the influence of the dark sector on them. So please start whenever.
Okay, all right. So good evening, and thank you very much to Professor Poe and Philip for this invitation to give this HEP seminar. I'm very happy to present my recent work. So let me quickly share the screen. And all right. So I guess you can see my screen now. And
Yes, we can see it fine.
okay, good. So just a moment. I need to. All right. So yeah. So today I'll be talking about large neutrino masses in cosmology with dark sector to the rescue. And this is based on a recent work which was done in collaboration with Thomas Schretz and Christina Benso at KIT. Uh, so starting with, as you might have noticed from the font itself, there's a slight Star Wars reference to the dark sector and dark side. I won't overdo it, but let's just start with the basic scheme. You have so many planets in the Star Wars ecosystem. And on the right side, you see the home planet of the Skywalker, which is Tatooine. So I would just use this to convert it into a landscape of BSM problems. So starting where the standard model is at the home, there are lots of areas and avenues where one can go beyond and explore the issues that we have, which are we have neutrino masses, dark matter, and baryon asymmetry of the universe, which the standard model doesn't explain. Now, neutrino masses and baryon asymmetry, it could be that their generation is at really high scales, whereas dark matter could be light or feebly coupled. Moreover, we could think of common frameworks where one could explain all these issues together. So maybe they have a common origin or there's a common frameworks. So I work on such models where you try to address all these issues, at least two of them in one framework. And today, the model that I'll be discussing later would also be based on such type of common frameworks which address two or more of these issues, right? So let's start with the dark matter in our universe. Just a basic recap of the properties that we assume in the standard lambda CDM cosmological model. So your dark matter has to be stable, which means it's long-lived enough that it produces the observed relic abundance. It has to be neutral, it does not interact with photons. We assume cold dark matter in lambda CDM, which means it's non-relativistic at temperatures around eV scale. Several observations from Big Bang nucleosynthesis and CMB have said that this is non-baryonic in nature, and finally, they have very weak self-interaction, that is, they're collisionless. We don't know the mass, we don't know the number density. We do have some theoretical limits on how heavy they can be. For fermions, it's roughly traced around the keV scale, whereas for bosons, it can be really, really light. So as you can see, it's the limit is about 10 to the power minus 22 electron volts. So for ultralight dark matter or wave-like dark matter, these satisfy. Now, of course, one can argue with all of these properties. One can assume that you can have dark matter decays, and then you can constrain your model. You can give it a very, very small charge. You can have hot dark matter. You can have warm dark matter. You can have self-interacting dark matter. So these are all the avenues where people build models and they try to go beyond these properties to address some of the issues that we have in the explanation. So starting with the very simple picture, which we'll use later, is that of the thermal lyrics, where you have a thermal freeze out of a weakly interacting massive particle, which are the WIMPs. The key assumption is that these WIMPs are initially in thermal equilibrium with the standard model thermal bath. when their interaction rates are higher than the Hubble expansion of the universe. Eventually, what happens is that this interaction rate drops below the Hubble expansion and they freeze out, giving us the relic abundance that we observe. And this freeze out is inversely proportional to their annihilation cross section. So this is representative by this diagram on the side, where in different directions you can extract different properties. So in the early universe, the annihilations lead to the freeze out, whereas at current times, these inhalations will what will give us the indirect detection signals. Whereas on the other hand, with this interaction, for example, if you go in the green arrow upwards, this is the direct detection signal that one can see of the DM interacting with a nucleus and then observing its properties. On the other hand, if you have standard model production of chi, then this production can be probed at colliders. So these are different avenues one tests, and there's still a lot of searches and probes going on. However, we haven't found anything conclusive. So one of the miracle or the astonishing properties of the scenario was that a weak scale type cross section was giving us the correct relic abundance. That's why this was called as the WIMP miracle, and it gained all the fame. However, we haven't, as I said, observed any conclusive evidence for WIMPs, which means we have to go beyond the standard assumption. There are other beyond WIMP scenarios or production mechanisms that one can target. So let's take a look at how we treat the dark matter in particle physics versus the visible sector. So with the standard WIMP that I just mentioned before, we assume that only one dark matter state makes up the entire dark sector. So it is responsible for the whole of relative abundance. And in general, you have some sort of stabilizing symmetry to make the dark matter stable. So you can either have a Z2 symmetry, for example, you can have a UN symmetry. In both the cases, your dark matter state are symmetric. And as I said, that the abundance would be set out, for example, by freeze out or freeze in. Now, if I contrast it to the visible sector, now the visible sector, which is roughly the matter content is roughly 1/5 of the dark matter content in the energy budget of the universe, as we see on the pie chart over there. You see that on the visible sector, we have several stable components and stabilizing symmetries, right? You have accidental lepton number conservation and baryon number conservation. And on the other hand, the abundance is set by the baryon asymmetry of the universe. So just comparing, so dark matter is 5 times more than the visible matter, which is known as the cosmic coincidence. And we see that the visible sector is quite rich, quite complicated in the sense they have a lot more symmetries and particles. So one can ask this question that why should there be just one particle on the dark side, right? So just argue on this basis that it could be that the dark sector is more rich. Apart from the DM, there are other states also with which there are more interactions that can take place. For example, you will have many degrees of freedoms. So if you have like an n component dark sector, if there are n components, they can have the following interactions. Of course, you have on the left, we have the annihilations to the standard model, but in principle, you can also have conversions between two components in the dark sector. Finally, two of them could meet with third one, and with the standard model, this is semi-annihilations. And then in the other case, depending on the mass splitting, they can also undergo co-annihilations, as we show in the fourth figure. The key idea is that such a complex system, which can be characterized by power laws and exponentials, which allow us to relax some of the existing bounds that we have from direct and indirect detection, as well as collider searches. So this was just as a motivation of what the dark sector means in the title of the talk. So some of the generic features that one gets is phenomenologically rich signals and relaxation of the existing bounds. Now, coming back to the other topic which was there in the talk is that of the neutrinos, right? So neutrinos in the standard model, again, a quick recap, the right-handed partners are missing, the masses are absent, they are electrically neutral, they interact only via weak interactions, and because of that, they are very, very difficult to detect. However, we know that neutrinos can change their flavor during oscillations, which has given us evidence that they have a very tiny mass. So this tiny mass, which I mean, in the standard model, they were assumed to be massless, but now we know they have a tiny mass. And that tiny mass, basically, the spectrum that we have is roughly 6 orders of magnitude smaller than the lightest charged fermion, that is electron in the standard model, which is further, let's say, 12 orders of magnitude suppressed compared to the top mass that we have in the standard model. Now, since the oscillation experiments measure only the mass splitting square differences, we do not know what the correct ordering is. So if your 1, 2, 3 is the generation index, you can define two schemes, which are normal hierarchy or inverted hierarchy, where the mass splittings that we observe from the neutrino oscillations are the atmospheric one and the solar one. So we don't know. We don't know what is the origin of such tiny mass. And further, we don't know what is the absolute mass of neutrinos. So this is one of the key points. That is the motivation behind this talk about the absolute neutrino mass scale and how they are measured. Finally, since we don't know what the origin of mass is, given that there's such a high order of magnitude difference in the fermion mass spectrum. So we go to effective field theory to explain neutrino masses, where we have the D is equal to 5 operator called the Weinberg operator, made up with the standard model lepton and Higgs doublet, which post spontaneous symmetry breaking generates tiny neutrino masses for your active neutrinos, which are suppressed by the scale of your new physics, which is lambda and p. And when you plug in certain values, for example, when you plug in the Higgs wave and you plug in the atmospheric mass splitting data, which is roughly 0.05 eV, you get that the physics scale should be about 10 to the power 14 GeV, which is close to the gut scale. And also, initially, what I had said about maybe this neutrino masses and baryonic symmetry, they're coming at really high scale. So physics at a really high scale is responsible for these tiny neutrino masses. Now, in this with the Weinberg operator, if you do the UV completions, you get the usual seesaws, which are your type 1, type 2, and type 3. In this talk, when I'll be presenting the model, I'll be presenting an extension of the type 1 seesaw, which is a UV completion, which involves fermion singlets, which are the right-handed neutrinos. And in type 2 and type 3, you have a scalar triplet and a fermion triplet, but we'll be focusing only on a type 1 scenario. Now, let's go to cosmology and see what happens there. But before that, yeah, okay. So before that, before going to cosmology, let's do a recap of what are the bounds that we have obtained from neutrino oscillation data. So since we don't know the absolute mass scale of the of neutrinos, we don't know what the lightest mass is. So you can you can define a sum of the neutrino masses for different ordering schemes, which are given by the equations shown here. Now, assuming that your lightest active neutrino is massless, you take M0 to 0, and you can clearly obtain these bounds for both normal ordering and inverted ordering, which has 0.058, so 0.06 electron volts and roughly zero point 0.1 electron volt in the case of inverted ordering. Now, so these two bounds that we have, you can see like in the case of inverted ordering, they're slightly higher than the case of normal ordering. The next question is, since we still need to probe the absolute neutrino mass scale, we do have some terrestrial experiments which are looking for this, and they are Catrin experiment in Karlsruhe in Germany, which is measuring the beta spectrum from tritium decay. And their latest results, they allow us, which they're sensitive to electron neutrinos. They allow us to put a bound on the sum of neutrino masses. So this is 1.35 electron volts. So you can see that this is already 2 orders of magnitude higher than what we saw in the case of neutrino oscillation data, right? So it's about 1.35 electron volt from the latest Catrin data. Whereas on the other hand, if your neutrinos are Majorana particles, in that case, they will also have signals at neutrinoless double beta decay. And the Kamlan-Zen experiment is probing that. And from the calculation, the spectrum there, one can put from the latest result this naive bound on M lightest to be about 0.08 to zero point 0.3 electron volts. So M lightest itself is kind of constrained to be on the bit of the higher side, which means that in conjunction with the oscillation schemes, when you calculate the sum neutrino mass bar, it will come out to be larger. So we see these are the bounds that one gets from oscillations, and terrestrial experiments is what we call as laboratory bounds. And the picture on the right side is quite interesting. It's the Catherine spectrometer that is being transported finally to the Culture North Campus, where the experiment is based. And I like the story a lot because this whole spectrometer was built together in this place called Deggendorf, which is just about 350 kilometers from Karlsruhe. But the transport of such a heavy device was very, very difficult, and they could not transport this on land. So they had to take the water route. And they traveled via the Danube River, going to the Black Sea, and finally going all the way, as the red path has shown, to reach Karlsruhe. And they finally did just a 7 kilometer journey on a road and took a detour of 8,600 kilometers. So I did this project when I was in Karlsruhe next to the Catherine experiment. So it's one of the cool stories that you get to see from particle physics. Anyway, so we see what the bounds from laboratory look like. Now let's see what happens in the case of cosmology. So in cosmology, at temperatures much higher than MeV, the weak interactions are in equilibrium, the neutrinos are in equilibrium. You can have neutron-proton conversions, which are mediated by these processes over there. And you can assume for the number density of neutrinos, we assume a Fermi-Dirac distribution, the fermions, and this serves us well. When the temperature cools down at the scale of MeV, these weak interactions, they drop out of thermal equilibrium. And the neutrinos, they decouple while they're still relativistic at temperatures roughly of 2 MeV. In this case also, it can be shown that it's well approximated to use a Fermi-Dirac distribution, but in this case, we just replace energy by the momenta as we show there. So it's a well approximated case. And then the energy density in neutrinos, they are characterized by N effective in this case. So here we show from this plot by Escudero different stages of evolution of the temperature of neutrinos in the standard model. So initially, when neutrinos are in thermal equilibrium, they have these neutron-proton conversions and weak interactions. They share the same temperature as that of the photon and the thermal bath. As we see at temperatures around 2 MeV, the neutrino decoupling takes place just slightly before the proton-neutron conversions freeze out. Once the neutrinos decouple, they still keep on sharing the same temperature as that of the photons. However, at later times, when electron and positron annihilate and they produce photons, this leads up to slight heating because entropy transfer, which increases this ratio of T gamma over. So the photon bath is relatively heated up compared to the neutrinos, which have decoupled already. And the temperature for the photon bath and the neutron bath that differs. So we have the CMB as the photon relic, and we also have a neutrino relic where their temperature ratios can be determined to be this factor. So once we know the CMB temperature, so from that we can determine the neutrino temperature, which in turn, from the formula that we had in the previous section for Fermi-Dirac distribution, allows us to compute the neutrino number density, which is 56 per centimeter cube per helicity state and per flavor. So this is what we have in the standard scenario. Also, please, if you have any questions, feel free to stop and ask me. I'll be happy to explain. So this is how we see that the temperature evolution of neutrinos takes place in this standard model. Now, let's go back to the comparison of this temperature and the masses of the neutrinos and how they come into play. So the cosmological observations are actually not directly sensitive to neutrino masses, but rather to their energy density. When the temperatures are much, much higher than the neutrino masses, the energy density is characterized by a number of effective species, which is given in terms of the radiation density and your photon density. Here you see that N effective is proportional to this momentum distribution as well as to the number density in neutrinos by this formula over there. And the standard model prediction is in very good agreement with the data that we have observed from plants. So this constraint is quite robust. This is a very good approximation, and we know that one cannot play much with N effective. On the other hand, when the temperatures are smaller compared to the neutrino masses, then their energy density, when they become non-relativistic, it can be characterized by their masses, and one uh, gets the energy density is proportional to the product of their masses times the number density. In this case, your neutrinos, they contribute slightly to the expansion rate as dark matter. And our plant data again gives us a constraint on this neutrino energy density over here, which is 1.3 to the power 10 minus 3. So this is how cosmology is sensitive to neutrino masses. Now, what are the effects of having massive neutrinos in cosmology? They affect cosmology mainly in two ways. The first is that they will alter the expansion history of the universe near matter radiation equality. So in the plot here, you basically see the omega, which is rho over rho c. You see omega scaling compared to the scale factor. And as we know that the Hubble parameter is directly proportional to the square root of this energy density. So neutrinos are very important in the evolution of the universe. They affect the expansion of the universe, which in turn also affects the perturbations of baryons and dark matter structure formation. Second thing is they have large free streaming strength, so they are very light and their thermal velocities are very, very high. So which means that it would affect the growth of structures, especially they will suppress structures at smaller lengths, as well as because of this, the gravitational potential is diluted, as I said, which will affect my dark matter and baryon perturbations. So here there is a simulation by Troil where on the left side, you see the simulation in increasing Z. You see the case for massless sum of neutrino masses is around 7 MeV. You can see how the simulation, you can see how smoothened out it is in this case. So these are the two ways, mainly two ways, how which neutrino mass is affecting cosmology. So the observables are CMB. So we have the CMB anisotropies, which are temperature fluctuations and large-scale structure of the universe. This can be seen from this review in PDG. On the left side, for example, for various values of the sum of neutrino masses, you can see the CMB angular for the temperature fluctuation. You see the suppression. Whereas on the right side, it's the matter power spectrum and the corresponding suppression compared to the case of massive neutrinos. So the larger the mass is, which means brighter line here, we see that it's more suppressed. So all in all, neutrinos, thus, their masses have implications for cosmology. And this allows us to constrain the sum of neutrino masses from various cosmological surveys. So I'm giving the two main ones. We have the Planck that I already mentioned. So Planck data, which takes the CMB and the baryon acoustic oscillation data set in 2018, placed this bound on sum of neutrino masses, which was 0.12 electron volts. And we recently, in fact, this year, we had the release from DESI, which is on, so Planck is CMB, DESI does large scale structure surveys. And from there, you see that the bound is more stringent. It's 0.06, about an order of magnitude smaller than the Planck one. It's 0.064 electron volts. So the masses, this is all assuming lambda CDM. These bounds are done assuming lambda CDM, and they are sensitive to the data sets that are being used. And one, of course, needs to correctly interpret and see what's going on and to derive these bounds. However, one of the trends that is clear, if we'll see, is that the bounds from cosmology are quite stringent. Moreover, with time, these bounds are getting stronger and stronger. In fact, there are some preferences from data sets which suggest that there could be a preference for negative neutrino masses, which we'll talk about later. So the key point is that these neutrino mass bounds, while they are good probes of neutrino masses in cosmology, them becoming stronger means they are in tension with the bounds that we showed from laboratory. So if I first compare my oscillations versus cosmology, and we do it side by side, you see for normal ordering, it's, as I said, 0.06 electron volts, whereas Planck bound is zero point 0.1 electron volts. On the other hand, if you take the DESI bound at face value, this is already very much in tension at 2 sigma level with the inverted ordering, right? So this is in significant tension, and it's quite close to normal ordering. Now, if you do neutrino mass model building, 2 zero neutrino masses which have quasi-degenerate neutrinos, they are predictable models, and all these models at least have a preference to have neutrino masses larger than 0.12 electron volt. So from model building side, for neutrinos, these strong bounds of cosmology are also in tension. Now, if I compare the same cosmology bounds with that of what we had observed from K train and from neutrinoless double beta decay, we see this tension, which is characterized in this figure over here by Thomas. So you have the Planck and the DESI bounds and their probability compared to the sum of neutrino masses. So the brown region is what is preferred by cosmology, whereas the blue shaded region is what is preferred by terrestrial experiments. So normal ordering, you see, this is the lower bound from oscillations, and note this is assuming that your M light is to zero. And we see that the inverted ordering is very much in tension with the bounds from cosmology. So the scaling has been shown on the left side with M0, which is the lightest active neutrino mass. So of course, if uh, if this is significant, both these bounds will be in tension with the current cosmological bounds we have. And further surveys and experiments, they are more sensitive to probe 0.02 electron volt regions. For example, CMB and Euclid, this is their projected sensitivity. So for placing this bound on some of neutrino masses, so this tension becomes large. And what this tension means is that if we have the standard lambda CDM model in this standard cosmological scenario, we might not observe the effects of finite neutrino masses in the laboratory. I mean, we want to detect them, we want to place bounds on them from the laboratory, but the experiments and the sensitivities that we have on Earth in terrestrial experiments, it is order of magnitude above what cosmology is telling us. So there is this discrepancy between laboratory and cosmology, and then you can ask, well, can the two be reconciled? Like, can we have some mechanism where the tension is alleviated, or if these cosmological mass bounds can be relaxed? This is very important for several beyond standard model scenarios, which are constrained by cosmological observations as well. Whereas also from a neutrino mass model building perspective, because if these bounds keep getting stronger, we might not be able to, for example, observe certain things that we are planning to with these experiments. So how can this be done? The idea is that in order for you to relax the cosmological mass bound, you need to do some modification. You have to go to some non-standard scenarios from the lambda CDM, and these modifications are done to the neutrino sector. So there's a class of all these non-standard scenarios, which is called as large new mass cosmologies. And there are several ways that this relaxation can be done. For example, starting with, as I said, that one uses Fermi-Dirac distribution for neutrino number density. One can have a modified momentum distribution where one doesn't, where you can assume that the neutrinos don't exactly follow Fermi-Dirac distribution. So that is one of the options, and how this number density can then change. And as we saw, that these cosmological bounds are sensitive to the energy density. So this, which in principle is the product of the number density times their masses. So if this momentum distribution is modified, my nu can change, and I would be able to relax the bound. The other thing is dynamical dark energy. So recent evidences from again this release is that we could have dynamical dark energy where lambda basically is not a constant but rather evolves with time. So here, what happens is that, as we saw, that massive neutrinos affect the thermal expansion of the universe, whereas this can be also mimicked by a dynamical dark energy that will also alter the expansion of the universe. And in these scenarios, the effect of neutrino masses that one sees in alteration can then be recompensated by a dynamical dark energy. So the sensitivity of cosmology to neutrino masses is then hidden, and this would allow us to relax the constraint on the sum of masses that we have. You can also have a time-dependent neutrino mass where neutrino masses keep changing with time from earlier times to now. On the other hand, you can also have neutrino decays. So in the fits and to obtain these bounds in lambda CDM model, your neutrinos are stable. But if they have invisible decay modes, for example, lighter neutrinos or some dark sector particles, then in principle, these decays and the corresponding neutrino lifetime is closely related to the neutrino mass bound, which together are constrained from cosmology. So neutrino decaying into some invisible particles would also mean that the direct dependence on neutrinos themselves is lost, because now the energy is carried away by their decay products. They will still contribute to the expansion of the universe. However, again, the effect of neutrino masses on these data sets and fits would be suppressed, allowing us to relax it. Finally, we have again modifying the number distribution of neutrinos or their population in the presence of dark radiation. So the stock basically is focused on having dark radiation to relax the neutrino mass bound, and I'll talk about it in detail. But just to give you an idea, these are some of the references which have opted for these non-standard scenarios to have relaxed neutrino mass bound. Just to give you an idea of how the bounds can relax, for example, for active neutrino decays, you can from 0.12, let me take the Planck result as a representative value, it can be relaxed to, for example, to zero point 0.4 electron volts in the case of active neutrino decays. For modified momentum distribution and time-dependent neutrino masses, this bound can go up to 3 electron volts. Whereas for dynamical dark energy, this one of the fits, they have about 0.25 electron volt. So all in all, what you can notice from these relaxed neutrino mass bounces that now they are compatible with what we saw from the oscillation data, as well as from the terrestrial experiments like catering.
Excuse
So
me.
what? Yeah.
Excuse me. So the numbers in red color in this slide, they are obtained from the reanalysis of the DAISY 2025 and the CMB.
Yes. So the numbers in this case is
Cosmological
at least.
bound. So they are all cosmological bound.
Yeah, these are all cosmological bounds. So in the case of dynamical dark energy, this particular bound is from the analysis of the DESI data.
Mm.
Whereas in the other cases, yeah, this again, I think these are more related with the Planck data set that was used. They modify the number density in these cases, and from there they obtain this sort of upper cosmological bound. But
Okay.
I don't think in these bounds they had considered the DESI data. I think it's only this one, which is quite latest in this reference over there, where they were able to relax it 2.25 electron volts.
Okay. Thank you.
All right, so I will be focusing on the presence of dark radiation and see how this helps us to have a relaxed neutrino mass bound from cosmology. Okay, so let's recap again. As we mentioned before, that the cosmological bounds are sensitive to neutrino energy density. When they're non-relativistic, your energy density is characterized by this product. And since this product is constrained from the Planck data to be smaller than this particular number, and this product involves the sum of neutrino masses and the standard neutrino number density, which we can then place the bound of this 0.12 electron volt that we had in Planck on the sum of neutrino masses if the neutrino number density is the standard one. So one can clearly see that if I reduce the number density of neutrinos, so if this number goes down, of course, the sum on the neutrino masses, this bound can be relaxed. This value can become larger. However, since I mentioned that when the neutrinos are relativistic, the energy density is characterized by N effective, which is where the standard model prediction is in agreement with what we observed from experimental data. So if you reduce the number density, this number reduction will also affect your N effective, which is also proportional to the number density. So somehow you have to compensate for this decrease in the number density of neutrinos. And that can be done if you add some light or massless degrees of freedom to your model, which is dark radiation. So this is one of the ways of how your reduced number density and presence of dark radiation can help us relax the neutrino mass bound. So one has to reduce it, but at earlier times where ineffective constraints of this were they're important, this decrease also has to be compensated. So how this works is that since we know that the neutrino decoupling takes place at 2 MeV, and the proton neutron freeze out is about zero 0.8 MeV at temperatures around 0.8 MeV. So the reduction post which the BBN takes place, the Big Bang nucleosynthesis, we have helium synthesis and other light elements. So this reduction in the neutrino number density should of course take place after BBN because the BBN predictions are very robust and we cannot modify that. So once these proton-neutron conversions have frozen out and neutrinos take part in that, we would require that the number density reduction in neutrinos takes place after this time period. So we take that the mechanism should be active at temperatures smaller or equal to of the order of 100 keV. What you do is you add a lot of BSM states, let's say X and Chi's, which will thermalize with your active neutrinos or the standard model neutrinos in this period. But then at later times, when we have recombination and we have the CMB, again, we have very nice predictions from it, which we can't modify. So our mechanism has to stop before this. So this thermalization of your neutrinos with these new states should only happen in this period so that we do not alter the successful predictions of both BBN and CMB. If you do this, if this mechanism gets activated in this period, your N effective will be unchanged at earlier times. So we are good with that. Post since and we are after doing this after the neutrinos have decoupled, the new states that are thermalizing with the neutrinos are basically their population is being produced at the expense of the population of neutrinos. So this in turn allows the number density of the neutrinos to be reduced. And the effective neutrino mass bound that one can get in this case is then given by the ratio of your current number density of neutrinos in your model compared to the standard model one. And this number density in your scenario will depend on your dark degrees of freedom. So it's better to understand it with this plot over here, which again shows the evolution of neutrinos number density with temperature. So as I said, you have proton-neutron freeze out at 0.8 MeV, then you have the BBN, the helium synthesis. So your neutrino number density, this is compared to the standard model value, cannot change in this period. Now imagine that you have a light boson in your BSM model that in the dark sector, which interacts with your active neutrinos. So this X boson is produced at the expanse of these neutrinos, which in turn then decays to these massless chi's, which are massless fermions, producing their population. Now, the interaction of this X boson is much, much stronger with these dark sector particles chi than compared to the neutrinos. So initially, this is produced from neutrinos, but then it mostly decays to chi's. So what happens is that your neutrino number density over time, once this decays of the boson go out of equilibrium, as I said, they have to be in this period, the number density of the neutrinos will decrease. And some of the compensation has been done by the population of massless guys that have been built. So from here, you can clearly see that N over N nu SM is about 0.1. So which means that this factor goes down to 0.1 in particular, then enhancing this value. So this is a characteristic scenario where how adding dark degrees of freedom and having interactions which have equilibrium with the standard model neutrinos can allow you to reduce the number density, and this is the core idea that one uses. So we have seen how the number density can be reduced, and we have seen how the compensation can take place by having these massless guys in this basic model, which is based on this paper by Escudero, Schwetz, and Terol, Calvo. Next question is that since we have a dark sector and we have a light-dark boson already, what about having dark radiation, dark matter, for example, right? So if you have a dark sector, it could also have a light keV fermionic dark matter candidate along with the dark radiation. And then you will have a rich dark sector, as I said, in the motivation before. So you have a dark matter component, you have a dark boson, you have dark radiation, and you have a multi-component dark sector. And since and we are talking about light keV fermionic DM candidate is because the temperature window that I have is between BBN and CMV is about the keV scale, and my light boson is also of order of few keVs. So we know that the keV scale sterile neutrinos are they are DM candidates. However, the production mechanism where they're produced from oscillations, in the standard case of Toddle's in vitro mechanism, where they're produced via small mixing with the active neutrinos, this is severely constrained. So here I show a plot from this paper by De Chuvia, Sen, Tangarife, and Zhang, where the white line corresponds to the Doddelson-Windrow mechanism that produces the correct DM relic abundance. But this scenario is strongly constrained and almost ruled out because of the X-ray observations that we have. However, you can have sterile neutrino dark matter if you have some non-standard interactions. So if you add some interactions where the neutrinos interact with, let's say, a neutrinophilic boson, either a scalar or a vector, they can open up this parameter space. In this particular case, they had a neutrinophilic scalar, and this space that opened up, this black region that you see, is then compatible with all the constraints that we show. Further, there are also strong constraints on thermal dark matter below the MeV scale, and this is again because of ineffective and other constraints from cosmology that we get. So usually when people make models of thermal dark matter, they have DM masses above the MeV scale. So in the case of KV scale dark matter, it was shown in this paper that you can have thermal dark matter below the MeV scale if it comes into equilibrium post neutrino decoupling. So if you have a mechanism where the dark matter particle comes into thermal equilibrium, but after the neutrinos have decoupled, then you are able to alleviate some of the constraints which allow you to have a KV scale DM in this region, and this fits as well. So the question is that in this case, that in this scenario, it is better if the temperature and the window, everything allows us, our dark sector can also have a DM particle. So now using all the concepts that we saw before about the DM freeze out, about type 1 seesaw, uh, non-standard neutrino interactions, presence of a dark radiation, it's time to build a model and talk about and give an example of how this relaxation works and what are the consequences of it. So one Star Wars reference, you welcome to the dark side where you have all these particles in there. So the model that we have is a minimally extended type 1 seesaw with a U1 symmetry, which can be both global or aged. In this case, the model is basically adding the standard model with three right-handed neutrinos, which couple via type 1 seesaw mechanism to the lepton and the Higgs doublets via the Yukawa couplings who I knew. But they also have Yukawa couplings to the dark sector where I have where I have a scalar phi and some fermions which are chi and psi, which at this Lagrangian level right now we take them to be massless. Uh, post phi taking a web, you'll see that some of the masses can be generated in the next slide. So along with three right-handed neutrinos, which will give masses to the three active ones, we also add another right-handed neutrino that, just to distinguish, we call it N prime, which is also very heavy, but comparatively less heavy than these Ns. And the Lagrangian, again, is parameterized. You have the Yukawa interactions, and notice that we do not include any of the mass terms for psi and chi. For in the gauged version, you can avoid these mass terms by imposing, let's say, a Z2 symmetry on the right-handed particles so that they are not allowed to be written in the Lagrangian. So you cannot have, for example, M chi L bar chi R, or similarly for psi. Finally, the gauge interaction that we have in this case, when this U1x is gauged, you will have a Z prime coupling to which is the boson associated with this U1x with the fermions and antifermions, in which case F is chi and psi. So you have these interactions. And you can define the coupling in terms of the mass of the vector boson compared to the web of phi, which is the dark, which I call the dark web. So this model actually is very similar to new lambda MDM model by Professor Cohen Tang, and that's how we also discussed before. However, their goals are different. They wanted to solve some of the problems with cosmology, like too big to fail. And in our case, we are using something similar, albeit with a larger dark radiation population to relax the cosmological neutrino mass bound. So
So,
key things to note here is that you have n chi generations of chi, and I add just one generation of psi, and we'll see why we do this. We have three generations of right-handed neutrinos and one generation of my n prime. So one can write the neutral fermion mixing matrix in this particular basis. So this is the light neutrino masses, which are zero. And you can define these parameters, which are just the Yukawa coupling times the respective webs. Now, in order to get the mass eigenstates, one has to diagonalize this. And since it's big matrix, you need to assume certain hierarchies that will allow you to simplify this. And that's what I was saying. So what we assume is that RHN mass M is much heavier than M prime. which is much heavier than the Dirac mass in the standard model, in the type 1 seesaw case, compared to the couplings, which are proportional to the dark web V5. If you look at the rank of the matrix, it's 2n heavy, where n heavy is basically the number of generations of n and n prime. And you will have about 2n heavy massive states, and you will have 3, which corresponds to the active neutrinos. And if you look at the matrix structure, you will have plus n light minus n heavy massless states. So basically what it means is, assume n heavy is 2. Let's say I only add one right-handed neutrino and another n prime. So we have n heavy as 2. And you have 3 active neutrinos, and let's keep n light as the light fermionic species that we introduced, which was psi and chi. So of course you will see that for 3 and with 2n heavy, you get basically one massless eigenstate, which corresponds in this case to chi, and this can be generalized to n generations. So we will, because of this structure, your n chi fermions are exactly massless. So they are massless. However, one of these dark sector fermions picks up a mass eigenvalue. This is the seesaw introduced Majorana mass. So the whole motivation of having, let's say, another n prime was to the 3 n's give masses, you can say, to the active neutrinos, whereas this n prime gives a seesaw-like mass to my psi. So since one of these fermions become massive, psi becomes the dark matter candidate in the model. And the mixing in this cases is then characterized in terms of the ratio of these parameters, where, as I said, lambda is defined to be in terms of the dark Higgs web, and your MD is the Dirac mass term in type 1 seesaw. So just for rough estimate, so with this mechanism, let's say if you have M prime of the order of a few GeVs or higher, you can, depending on the web of the dark sector, you can generate a KV scale dark matter mass. So we have, with this UV complete model, in a sense, achieved n chi generations of massless fermions as well as one massive dark matter component. Sorry,
So one question. In your model, this new fermion, dark fermion, Dirac fermion, or so in the
So the dark fermions, yeah.
yeah.
So we introduce these vector-like fermions. So for the case of chi, you have chi L and chi bar, and so they are vectors. So both of them will contribute. So both chi L and chi R contribute. In this case, for the dark matter, actually, so since we have this, we said we impose the Z2 symmetry on the right-handed component to forbid their masses. Only the left-handed component becomes massive. So your dark matter is basically a Majorana type fermionic dark matter, whereas psi R still remains massless, and along with these n chi's will contribute to the dark radiation. So yeah, that's a good spot, that only the left-handed component here is getting the seesaw type Majorana mass, and the others you have chi L and chi R contributing, whereas psi R contributes to your dark radiation, right? So once you have this, we can look at the production and freeze out of the DM candidate, because we want to build on that concept. From the interaction Lagrangian that we had between the Z prime and this pair of fermions, we see that you can have these sort of couplings, which are in turn proportional to the mixings that was described here. So this mixing needs to be small. And the other mixing, which is between nu and psi, and we now know psi is the DM, this needs to be really suppressed. We'll see why. Whereas this mixing is supposed to be small, and which will give us the key features that we wanted. So one can generate all these interactions. And now we see that now, just like we saw in the picture before, your neutrinos via, because now your Z prime interacted with chi's and psi's, and now that they mix with neutrinos, you also have this Z prime nu interaction. So they produce it via this mixing, and this is suppressed. Whereas the production of chi-chi and psi for Z prime, for example, is of the order of G, the gauge coupling in the dark sector, and depends on the mass of the Z boson and the wave of phi. So in the same way, your dark matter can be produced from direct decays if it's more mass, if this mass hierarchy is satisfied, or from 2 to 2 scatterings of this example. Since we have we have dark radiation, of course, your DM will annihilate to them, and their number density of whatever is produced will decrease, and they will eventually freeze out when the dark sector temperature will be smaller than the mass of psi. So you have to see it in this way. It's the same picture, but now with the presence of a dark matter candidate. So initially you have the neutrinos, which have decoupled, and the production of the new species takes place on their expanse, producing the Z prime boson, which in this case, both chi and psi are produced via decays. And now the whole equilibrium system is characterized by a different temperature since it's interacting with the dark sector. So this is all characterized by the dark sector temperature. Here, of course, in this particular plot, I show it in terms of the photon temperature. But anyway, you see that once the DM is produced, once the mass drops below the temperature drops below the mass, these annihilations will freeze out and you will end up with a dark matter relic density. And then you can, from the relic abundance, you can constrain the masses and the interaction. So this is the standard picture that for dark radiation in the presence of a dark matter. Again, we have that same suppression of the limit and the sum of neutrino mass bound and the compensation by dark radiation. However, this freeze out, as I said, is now in the dark sector. It's analogous to the visible sector freeze out, but now it depends on the dark sector temperature. For the two annihilation channels which we have for different mass hierarchies, here I show contours of relic abundance in the MZ prime and M psi plane. So you can see that the mass range that I'm targeting for DM is from 10 to 1000 kV, whereas the Z prime is also, yeah, more or less we are around order 100 kV or so in this plot. The dots actually correspond to the numerical solutions that we obtained from solving the Boltzmann equations for the evolution of all number densities. A good thing about this relation for these annihilation cross sections is that in the extreme limits, the annihilation cross section is inversely proportional to the fourth power of the dark wave. And one can then just have a clear dependence from relic abundance just on how much the wave of your dark phi should be in these two limiting cases. So because of this, the model becomes a bit predictive in the sense that we have it from, we can constrain V phi from producing the correct relic abundance. Now, as I said that we have dark radiation. In this case, similar to the sterile neutrino dark matter scenarios, you can have DM decays if your M psi is smaller than MZ prime. And the constraint usually is put that the DM lifetime should be larger than the age of the universe, so that they are stable on cosmological time scales. Usually, you will also have psi to 3 new decays, but here the chi-chi ones are much stronger because they are suppressed only by by 2 powers of this mixing angle, which can be characterized again in terms of the wave of the dark Higgs. And this relation, as you see, tells that the mixing angle needs to be really small in between the dark matter and the neutrinos, not the other mixing angle where the new chi that we saw can be comparatively larger, which allows us to have this feature of producing the correct relic abundance as well as for the dark radiation. So this mixing angle, I mean, we need it to be suppressed from the stability as well as from X-ray bounds. In both the cases, we see that, I mean, even if we put it to 0, it doesn't harm the model, but we just keep it there so that, yeah, we do not cancel it by hand. In the second case, when the decay goes to z prime and nu, in case this hierarchy is satisfied, of course, there are much stronger constraints because this is a two-body decay compared to the three-body one. So which means, okay, it's better if I can suppress, maybe if this could be done if you add some other discrete symmetry to completely suppress this sort of interaction. This is not very relevant to the model. Similarly, we have constraints from the observation of monochromatic X-ray lines because of this mixing between the sterile states and the active states. And this gives me a constraint on the mixing angle for a DM of mass 15 keV to be the square to be less than 10 to the power minus 13. So we see that if the bounds from stability are satisfied, then the X-ray bounds are automatically satisfied. Finally, as in any warm dark matter model, there are strong constraints from structure formation, which will be there in our case as well, because this is because of the large free streaming scale, which again prevents formation at small structure scale. To evaluate these constraints, one has to take into account that you have the DM annihilations, which drop out of the kinetic equilibrium once these interactions freeze out. But the DM will still remain in thermal contact with the dark radiation via these elastic processes such as psi chi to psi chi. And it is this decoupling temperature, this is the temperature of kinetic decoupling, that one needs to determine in order to calculate the half mode halo mass, the mass at which the power spectrum gets suppressed by half compared to the standard case, and which is related to this length scale, which is called lambda half mode. Here, which from different references, which we take 0.1 megaparsec for estimates, which is a good enough estimate. And using these bounds, we see that depending on the number of dark degrees of freedom, as in massless dark degrees of freedom. So this is G prime means you have to multiply it by, so there are four because they have you have psi L, you have sorry, you have psi R, you have chi L, chi R. So this this roughly corresponds to like 10 generations and so or 40 generations and so on, if that much as you add. What we see is that for both the scenarios, depending on whether m psi is larger or smaller than mz prime, it is possible to have DM masses larger than 10 keV, which are allowed by structure formation. So this works for us well. Then there are all the other constraints that I discussed in the sense for the mechanism to be active between the CMB and BBN period. First, of course, we have the constraint from thermalization. We want that these active neutrinos thermalize with the Z prime in this particular temperature window, that is after BBN and before CMB. So in the red region, this coupling, this interaction of Z prime with nu is not strong enough for them to thermalize in this period. So it's excluded from this. Then we have constraints from new decouplings because we do not want them to thermalize before BBN, which will alter the predictions. So this blue region is then excluded by this particular bound by demanding that these nu with Z prime interactions drop out of equilibrium at temperatures above 0.7 MeV. Now, if a small population of chi gets produced, then you also have these kind of processes which can lead to the exponential growth of chi's. And one also needs to ensure that they go out of equilibrium at temperatures above this. So this darker blue region shades out, removes that part of the parameter space. Finally, we have constraints also from the CMB. We want that these interactions, which we're producing Z prime and we're leading to the thermalization, they all need to be inefficient at a redshift around 10 to the power 5 so that our CMB is not perturbed by the lack of chi free streaming, which along with these 1 to 2 processes, one also has to take into account these chi to chi elastic processes. You have to make them both inefficient at CMB time scale. So this excludes the green region in the plot. So as you see that in this plane, which is in the KV plane, the white parameter space is what is allowed. It's closed on all the sides. We show the contours of relic abundance for different DM masses, 15, 50, and 100 keV, where the dark matter relic abundance is satisfied. This line here corresponds to this mass hierarchy between mz prime and m psi, where mz prime greater than 2 m psi or less than that, where it can either be produced directly in decays or via 2-to-2 processes. We see that the area around here, which roughly indicates that like a web of about a GV should be in that region from zero point 0.1 to 1 GV, is where the correct dark matter relic abundance is satisfied, and it's also okay with all the constraints. And this is for a particular value of my new chi mixing, which I take 10 power minus 3. You note that it is much larger compared to what we saw for the DM neutrino mixing. If you take higher values of theta nu chi, there is actually a constraint on how large or how small this theta nu chi, as in the mixing between neutrinos and your dark radiation component, can be. And this is constrained because your chi's can then be produced from neutrino oscillations, and that too before BBN, which will then modify your N effective. So by demanding that delta N effective within the constraint, within the limits is less than 0.3, we observe that your mixing angle between nu and chi should be between 0.1 to 0.0001 cases. However, we find that for the extreme cases like 10 power minus 1 and minus 4, there is no viable parameter space. But for 10 power minus 2, we do get some viable parameter space, though a chunk of it, as you can see from the left side, is excluded because the chi's can be produced for these large values of mixing angle by oscillations and then contribute to an effective more than 0.3. So these are basically the main results of how you have a mechanism where you are able to relax the neutrino mass bound as well as accommodate a KV scale dark matter candidate, which is okay from all the constraints from BBN, CMB, as well as for the mass values of DM from structure formation. So this is the main parameter space viable for the model. Next, we look how the neutrino mass suppression takes place in these models. So your new degrees of freedom now come into equilibrium with the neutrinos. And let's say that the neutrinos have decoupled, this is their temperature, and now everything comes into equilibrium. And let us assume that it instantly comes into equilibrium. And they form a thermal system, which is now characterized with this temperature TEQ. You can use conservation of energy to write this relation where F is nu, chi, and psi, and then you have the contribution from Z prime. Finally, the system will evolve to a final temperature adiabatically when both your DM and the Z prime will become non-relativistic, in which case one can use the conservation of co-moving entropy to relate the final temperature once these guys have become non-relativistic and you only have the dark radiation component, to get a ratio of the temperatures, which allows us to determine the Nu in this model compared to the standard case in terms of the dark sector temperature and the standard model neutrino temperature. So two things are modified, of course, the number density, and also when you have these many degrees of freedom, of course, there will be contribution to N effective, which is proportional to the dark degrees of freedom, the massless dark degrees of freedom that you add. And note that this reduction, which now is based on dark sector temperature, which in turn depends on the degrees of freedom in it, is what goes into your neutrino mass bound from cosmology. So you relax this. This is what cosmology puts a bound on, is what you observe. And your sum of neutrino masses for this becoming small can then be proportionately increased. We show the plots depending on how many generations of massless fermions chi you add, how much suppression of mu you can achieve, the contributions to delta N effective, as well as the temperature ratios corresponding to N chi. You see that very small generations are, they have much larger contribution to delta N effective, which is kind of excluded from the Planck 18 results. In the future sensitivity of upcoming experiments, for example, CMB S4, can tightly constrain it and make it more predictive. So the slight increase in delta N effective is kind of a signature of the model, whereas the suppression, as we see for larger generations, you have more suppression. This is seen best from some benchmark points where we show that, assuming the hierarchies that we used for the simplification, how for a DM mass that you have of like roughly 10 or 100 kV and your heavy right-handed neutrinos quite massive, you can relax the neutrino number density. So in compared to the standard model case, about 1/5 if you add about 10 generation, and about 0.2, 0.135 if you have 20 generations. And the corresponding increase in delta N effective is also shown here, which is consistent. So a decrease in this NU by 0.2, which is 1/5, means that your neutrino mass bound from Planck, which was 0.12, can be relaxed to become 0.6 electron volts, for example, which is then okay with, is not then in tension with the oscillation data for normal ordering or inverted ordering. So yeah, that was it, how you can have everything together. So let's wrap it up. We are entering a precision era for neutrino cosmology with of course DESI and Euclid and CMB-S4 to come. So understanding how these cosmological mass bounds and neutrinos come from this, how the data sets are analyzed, how BSM signals are or can affect it, will allow us to get a better understanding, as well as leads to hints of what new physics or what non-standard can be used. So that's why it's always a good exercise to keep building the synergy between cosmology and laboratory. In this particular example that I gave, we focused on the presence of dark radiation to relax the cosmological neutrino mass bound, and not just dark radiation, we had an expanded rich dark sector where we also accommodated a KV scale sterile neutrino dark matter candidate. We presented a UV complete model, so everything, all the parameters, we presented in an extension of type 1 seesaw, where for, of course, I presented you can have neutrino masses and you can have dark matter. But given the high scale of your right-handed neutrinos, as we saw in some of those benchmark values, one can also do leptogenesis, and then you will be answering all the three problems in the same framework. Now, one might think that, of course, I'm adding too many generations of my massless fermion sky. So the model has a very complex particle content, but in terms of the free parameters, what really control the parameter space, they are not too many if I assume that the interaction strength to each chi generation is the same. So it's just characterized by one mixing angle. So at the end, I only need my Z prime boson mass, the phi web, the dark matter mass, the mixing angle, and how many generations one had. Thermal dark matter below the MeV scale is possible if they come into equilibrium post new decoupling. As we saw, we were able to satisfy the relic abundance and structure formation constraints. So in this case, the signatures that maybe can be probed at future experiments is the slightly increased N effective at late time. So with this sensitivity, we might be able to rule out how many generations are actually allowed or not in these kind of scenarios where you add dark radiation, and suppressed matter power spectrum because of warm dark matter, as we saw in the constraints from structure formation. So yeah, that was it. Thank you very much. And if you have any questions.
Yeah, let's thank the speaker for the interesting talk. And are there any further questions? Okay, well, let's thank you for speaking to us today. It was very interesting. And we hope to see you in person maybe in the future.
Yeah. I would be very happy to visit. Sorry. Yeah.
Okay, thank you very much.
Yes, sometime
Very
in the
nice talk.
future. Yeah.
Yeah, very impressive. Yeah, I enjoyed your talk very much.
Thank you. Thank you. Yeah. It was good and